much shorter talk, and I'll also go a little bit slower than I did yesterday. So I'm just going to talk about forces, how you calculate them, and some of the things you can use them for. So yesterday we already heard from Stefano Baroni about the Hellman-Feynman theorem, but I'll go over it again because it's the most important thing we need to know for forces. I mentioned stress very briefly, but in the next talk we will discuss stress in more detail. Then talk about techniques for minimizing a function, which you then use for geometric optimization using forces. And then I will also mention two other things you can use forces for. One is what are called frozen phonon calculations, and then the other is molecular dynamics, which also I'll mention very briefly because next week you'll go into it in much more detail. So start with the Born-Oppenheimer approximation, which we also heard about yesterday. And these are the guys who came up with it. So we know that the many-particle wave function is a function of both nuclear and electronic coordinates. And what they suggested we could do is separate out the Hamiltonian into a nuclear part and an electronic part. And then when you have a separable Hamiltonian, then it's easy to write the wave function as a product of two parts. So you can write the overall wave function as the product of a nuclear part and an electronic part. And the reason why this is okay to do is because the electrons are much lighter than the nuclei. So to first approximation, you can think of the nuclei as being fixed and immobile on, sorry, this shouldn't be nuclear, this is electronic motion, I apologize. So we need force. Forces are a very useful thing to have if you're doing an electronic structure calculation. One way you could think of doing it is to do it as finite differences. So yesterday we saw that you can calculate the total energy using a density function theory calculation. And you can think that if you want to calculate the force, say you have a diatomic molecule and you just separate out, you separate them by some distance, you extend the bond by some distance x, you calculate the energy, the change in the energy, and then you divide that by the amount you stretched it by, and that can give you forces. And this is something you can do, but it's very expensive to do because you have to repeat your DFT calculation at each new position. And instead, one can use what's called the Hellman-Feynman theorem. And this was actually Richard Feynman's senior thesis when he was an undergraduate. So this is the paper in which he wrote it, and but it had also independently been discovered around the same time by Hellman. So what does this theorem say? It says, now supposing you want to calculate the force on an ion. We say ion because we separate out, when we make this pseudo-potential approximation, we separate out the valence electrons, and then the nucleus and the core electrons together, we call that the ion. Okay? So this capital I labels ion. So the force on an ion, you have to find it, you have to take the derivative of the energy, and the energy is given by the expectation value of the Hamiltonian in the wave function. Now, when you operate on this expectation value with this derivative, you get three terms depending on which term your derivative acts on. So you have this term where it acts on the middle term, and then you have these two terms where it acts on this, on the bra and the ket. Okay. However, when this psi is an eigenstate of this Hamiltonian, you can then say that H psi equals E psi. So you can operate it once over here and once this way. Okay, so we make this substitution. And I'm going to the next slide. So here, what I've done is I've pulled out this E because I had the Hamiltonian acting on psi, and I can pull it out, and the same thing over here. But these two terms together would be what you'd get if you operated with the derivative on psi capital psi. Okay? But this quantity is equal to 1 because the wave functions are normalized to 1. And therefore, its derivative is 0, so you can drop that term. And what you're left with is this. Okay? So, in what we had before, we would have to evaluate this Hamiltonian and then take the derivative at different ionic positions, to do which you would need to calculate this quantity at different ionic positions. But what we have instead now is this expression where the derivative acts only on the Hamiltonian operator, and you evaluate the expectation value only at the position that you're at. So now we can calculate the force from a calculation at one configuration alone, which is a huge savings in time. So this is the same thing that you saw in Stefano Baroni's lecture yesterday, except he did it in general for some parameter lambda that the Hamiltonian depended on. And here I have done it specifically for the case where lambda is the ionic coordinate. If the bases happen to depend on ionic positions, that is, if you had written the wave function as a superposition of some localized orbitals, which would be centered, for example, at the nuclear positions, then you would have additional terms in your derivative. But we don't have that because we're using plane waves as our basis, and plane waves are independent of position. So if you did have localized orbitals, you would get additional terms, and those are called the Coulomb forces. Okay? So this is one of the big advantages of using plane waves as a basis for your DFT code, because you can calculate forces very easily. You don't have these additional terms. And notice, to get this, we had used the fact that this psi was an eigenstate of the Hamiltonian. Okay? And if that were not true, we wouldn't have been able to get this formula. So when we do our DFT calculations and we calculate forces using this formula, you have to be very careful that you really have converged your SCF calculation very well, because if you haven't done that, then you will find that, and then you use this formula to evaluate forces, you will get errors. Okay? So when you use this Hellman-Feynman theorem to calculate the forces using, for example, the PWSCF code, what you have is, you have, again, this is the same expression I had before. This PO is just to tell you that you're making the Born-Oppenheimer approximation, and you would get these two terms. This is the potential, the external potential, which in our case is the pseudo-potential due to the iron cores. And this term here, it represents the interaction of the ions with each other. And I just will mention this very briefly because it will be talked about in the next talk, that when you strain a crystal, that is, you change the positions from some original value to a strained value, then you have a quantity called a stress tensor, which is given as a derivative of the total energy with respect to the strain, and very similar to the Hellman-Feynman theorem for forces. There is also a stress theorem, which was shown by which was proved by Nielsen and Martin, that you can also calculate the stress at a single configuration. And why is this useful? You may have, so supposing you want to optimize, say, your lattice constant. So yesterday we had looked, for example, we calculated the total energy of silicon at a number of different lattice constants. And we didn't choose to calculate the forces, but if you were to go back now and rerun those calculations with the flag telling you to also compute the forces, you will see that your force will be 0 at every lattice constant. The forces on the atoms in your unit cell, and that is because of symmetry, even if you're not at the right lattice constant. However, if you were to calculate the stress tensor, that would be 0 only at the equilibrium lattice constant. So you can use the stress tensor to optimize the cell size, and Stefano De Girompoli will talk about it in the next talk. So when you're running PWSEF, if you want to compute forces and stresses, you just have to turn these flags on. So this is to say whether you should print forces, and you have to make that true, and this is whether to compute stress. And if you are doing a calculation where you're going to relax the ionic positions or molecular dynamics or something for where you obviously need forces, then you don't need to bother to set it on. It will be automatically set to true. So here I've just shown an example of what kind of output you get when you compute forces with PWSEF. So this is a calculation which Kanchan Ullman, my student who's here, did for graphene, where he made a vacancy so that there's one atom missing over here. It should have been here. And this is without relaxing the ionic position. So you freeze all the atoms and you remove one atom to create the vacancy. And then you see that you get in your output forces that act on all the atoms, the X, Y, and Z components. In this case, the Z components are 0. And you can also visualize that using X-Cris-Del, and that's this picture here below. So you can see that you have all these green arrows are a measure of the forces that are acting on the atoms. So clearly, it's not in equilibrium, and then you would like to use the information contained in these forces to move the atoms until you achieve equilibrium, which is when all the forces are 0. So I'm going to just mention 3 things you can use forces for. One is to optimize ionic positions, which is what we call geometric relaxation. You can also use forces to get information about force constants that couple atoms with each other, and so from which you can get vibrational frequencies, and then you can use them to do molecular dynamics. So let me first talk about geometric relaxation. So what we want to do is we want to move the atomic positions until the lowest energy equilibrium configuration is obtained, and at equilibrium the force on every atom is 0. Okay, so the force for all the ions, you have the force equal to 0. And looking for such a configuration is equivalent to searching for a minimum in your 3n dimensional space, where n is the number of ions that you have. Okay, so we have some energy landscape, this 3ni dimensional energy landscape, and we're looking for the minimum in this landscape. So in order to, this problem of minimization is something that one encounters a lot when one is doing an electronic structure calculation. One of the reasons you need to minimize is what we're talking about now, which is optimizing ionic positions. But also, if you remember correctly, if you remember from yesterday, when we solved the Kohn-Sham equations, we're actually looking for it's equivalent to minimizing the energy functional. And I had also mentioned in passing yesterday that when you diagonalize the Hamiltonian, in that step you can recast this diagonalization problem as a minimization problem. So you can use the techniques of minimization there. And the other context in which we see it is when we're mixing. So if you remember, I had told you yesterday that when you're doing the self-consistent loop, if you get an output density at one step, if you just feed it in directly as the input to the next cycle, you will not usually achieve self-consistency, and you instead take some combination of the output and input densities, which we call mixing, and that also you can view it as a minimization problem. So I will just very briefly talk about some numerical methods that you can use for minimization. I won't go into too much detail, and I just wanted to mention that the convention I'm using in this section of the talk is that subscripts refer to coordinates and superscripts to iterations, because this minimization is something you do iteratively. Okay, so supposing we have some function f of x in one dimension, I've just drawn it schematically here, and you are searching for the minimum. So of course, if you knew the functional form of f of x, it would be easy. You just take the derivative and find out where the derivative goes to 0. But supposing you don't know some simple functional form. So the only way you can evaluate the function is you take some position and then you evaluate the value of the function at that position. Now, supposing we also had an easy way of evaluating the gradient at a particular point, then you can use the gradients to find the minimum. So for example, supposing you start out here, okay, so if you calculate the gradient here, it would actually point that way, but we take the negative gradient, so that would point this way. So if you were to think of this as an energy, for example, then the force acting on the particle would be to the right over here. And you move a little bit in the direction of this force. So supposing you were to come here, then again you repeat that, you would come here, again you repeat this, and you keep repeating this until you come to a point where your gradient is 0, and you say that's the minimum that you are searching for. So one can write this as the n plus 1 position is the nth position, and then you evaluate the force at that nth position, and you move it in the direction of that force by some amount beta. Okay, so you come down by a bunch of small steps. And you have to choose this beta in some nice way, because if it is too small, it's going to take you forever to inch your way along to the minimum. But if it's too large, you're going to overshoot. Okay? So the problem with this algorithm is that it can take you very long to find your minimum. So the next thing one can use is what's called the Newton-Raphson method, which was initially formulated by Newton as a way of looking for the roots of a function. Okay, so here is some function, and we're looking for the root. That is, we're looking for the position at which the value of the function becomes 0. And how you do that is you draw, again, you take the slope, the tangent to the function at your present position. Now, you can easily find out where the tangent, this line crosses 0 by just using this equation for the slope. And then you make this the subject of the formula. So your n plus 1 guess for the position is related to the nth guess in this way. Okay? And then you would come to this position, and then you would go here and you would repeat that procedure until you finally come to a position where the value of the function is 0. And notice that in order to do this, you again need to have some way of calculating the first derivatives. And if your function were linear, then you would converge in one step itself. Okay? But we can trivially recast this as looking for a minimum rather than looking for a 0, because looking for a minimum in some function f is equivalent to looking for a 0 of f prime, where f prime is the first derivative. Okay, so now I have written exactly the same equation as I had on the previous slide, except there where I had f, now I have f prime, and where I had f prime before, now I have f double prime. Okay, so this is your equation, and once again, if you want to, you needn't move entirely by this quantity. You can have a step size later. Okay, now notice that this, in order to use this formula to find the minimum, you need to know first derivatives as well as second derivatives. Okay, and in the previous slide, I had said it would converge in one step if f were linear. So now, in this slide, it would converge in one step if f prime were linear. But that's equivalent to saying if f is quadratic. Okay, so this is a very good algorithm if you have a quadratic form. So now we'll go from one dimension to n dimensions. So you have n variables, x1, x2 up to xn, and you're looking for the minimum in this multi-dimensional space. So where you, instead of having just a first derivative, now you have a gradient vector. Okay, and we want to find this x naught. This x naught is in boldface to say it's a n-dimensional coordinate. And we want to find the position where this f has its minimum value, that is the point at which the gradient is 0. And again, in the same way, you find it iteratively through a sequence of points in the n-dimensional space that are sort of stepping stones to your finding the value of the minimum. Okay, so I had said before that you could in the one-dimensional case, I said the easiest thing you could visualize doing is just taking little steps in the direction of the force. So you can do that again here, and this is what's called the method of steepest descent. So at every point that you are at, you find the gradient, and then you take a little step in the direction opposite the gradient. So here, this is just some notation where minus of the gradient is written as capital G. So you can do this, or you could do something that's one step better, which is once you have found the direction of the gradient, you actually search for how much you should move along that direction by doing a line minimization. So we already talked about how to find a minimum in 1D. So you follow that procedure and you find the lowest point, line point, in that direction. And then you repeat this. Now, so this is shown in this particular case for a two-dimensional function where you start here and this is the minimum, and by steepest descent you find your way to the minimum. This can be slow, and part of the reason why it doesn't work very well is that you have found the minimum on along one direction, but then when you move in the next direction, you can lose some of the minimization that you had achieved in the previous direction. Okay, so there is this method called conjugate gradient, which is designed so that when you find the next direction along which you are going to find the minimum, it doesn't interfere with whatever minimization you have already done along previous directions. But I'll just say, okay, so we said that the first derivative in your n-dimensional space is the gradient. And for the second derivative, you have what's called a Hessian, which is a matrix. It has n by n elements, where capital N is the dimension of the space in which you're searching for the minimum. So it's given by these second derivatives. Okay, so what the Hessian tells you is it gives you information about the curvature of your function in this n-dimensional space. So now let's try to extend the Newton-Raphson method, which we had in 1D, to n dimensions. So I apologize. I guess I was feeling kind of silly, so I put a smiley face at the position of the minimum. So in 1D, this is where you are searching for, and in 2 dimensions, you would like to find that position, and in n dimensions, of course, I don't know how to draw it. So this was the formula that we had in 1 dimension for successive updates, which you hope will eventually enable you to reach the position of the minimum. Now we're just going to extend that to the n-dimensional case. So where we had a single variable x, now you have this n-dimensional vector x, where you had f prime, you have the gradient, and where you had 1 over f double prime, you would replace that with the inverse of the Hessian matrix. Okay, so we just make these substitutions, and we end up with this formula, which says that the n plus 1 guess for the position is given by the nth guess minus beta times, this is again the step size, this is the inverse of the Hessian, and this is the gradient. Okay. So we can use this in n dimensions, but the problem is that in order to use it, you need 2 things. You need the gradients, and you also need the inverse Hessian. Okay. So now let's go back to the physical problem. Maybe I'll go this. Sorry, I'll do this slide first. So, is there a way that, supposing it's easy for you to compute first derivatives, which are the gradients, but difficult to compute second derivatives, which are the Hessian or the inverse Hessian? So, is there some way you can avoid computing this inverse Hessian? So what you can do is that since you are, as you're moving along, you are calculating the gradient at different places, you can use that information to make a guess about what the second derivative is doing, because you have some information about how the first derivative varies as you go through your space. So if you do that, then it's called not the Newton-Raphson method, but a quasi-Newton-Raphson method. And there are different prescriptions. So it's an underdetermined problem. There's no unique way of building up your approximation for this inverse Hessian. So there are different formulae one can use. And one of these is referred to as, okay, so over here I still have really just the formula I had for the Newton-Raphson method. I just rewrote it slightly so that here I have that vector and here I have normalized it. And you would like to move, instead of where I had beta before, I have some quantity rho, which is, you can think of as a thrust radius. You would like to move as much as you can, but if you move, okay, so if your function were a quadratic form, then this would be exact. So what you do is you try to move within the neighborhood of where you are, where you feel it is valid to say that it is quadratic. Okay, so that's what this thrust radius is, and here there's this horribly messy formula for this approximation for the inverse Hessian. So obviously nobody is expected to remember it. And I decided that since the formulae got too messy, we'll stop here about numerical methods and go back to our problem. So what we have a function f, which we want to minimize. In our case, that function is the total energy. And the points x in this 3n dimensional space are the coordinates of our ions. So x1, y1, z1 are the coordinates of the first ion, then the second ion, etc. Now, the gradients that we are computing are the forces, which we said it was easy to compute using the Hellman-Feynman theorem. And so it was easy for us to compute first derivatives using the Hellman-Feynman theorem, but we don't want to compute the second derivatives. And so we will make the BFGS or some other approximation for the inverse Hessian. So we will use some minimization scheme to find the ionic positions that give the lowest value of the total energy, which is also where the forces on all the ions are close to zero. So how you do this in the PWSCF code is everything in this blue circle is the loop that we used yesterday and that I showed you many times. So that's our SCF loop. And we now put that within an outer loop. So once we've achieved self-consistency for a set of ionic positions, we see if the forces are zero or not. If they are zero, your structure is optimized. If they're not, then you have an outer loop where you move the ions and you keep moving them until you finally achieve minimization. So whatever scheme you use for minimization will come over here. So to do this in PWSCF, so yesterday in the very first name list, the control card, we had said calculation equals SCF. Now instead you put calculation equals relax. And you can use the BFGS algorithm for finding the minimum. Or you can also use what is called damp dynamics. And I won't discuss that, but Stefano will discuss that in the next lecture. So the other thing you have to do when you're doing an ionic relaxation is you might not want to optimize in all three dimensions for every ion, either because you know by symmetry that it's not going to move, or for some reason you might not want to allow it to move in certain directions. So for example, here is the positions for a 4-layer aluminium 100 slab. So this is 4 layers of aluminium atoms stacked along the 100 direction. And if you want to find, you say that these two stay at the bulk-like positions, these 2 layers, and you just want to move the position of the top 2 layers. And by symmetry, you know they're only going to move along the z direction. So therefore, for the last 2 atoms, after you put the coordinates, you put 0, 0, 0 to say that they shouldn't be allowed to move in any direction. And for these 2, you put 0, 0, 1 to say that they are allowed to move along the z direction. And I just wanted to mention that the techniques that we're talking about, they enable you to find a minimum, but they do not necessarily enable you to find the global minimum, which is a very, very hard problem. Okay? So you might, if you have reason to suspect that you have a complicated energy landscape with a lot of minima, then you should start with lots of different positions and see if they all relax to the same final state or not. And this I just, as an example, I put it from one of our papers where we were looking at nitrogen monoxide on a rhodium cluster which contained 5 atoms. So you have 7 atoms whose positions you want to find, and so you have 21 coordinates. So you're looking for a minimum in this 21 dimensional space, and you find lots of different minima. So these are some of the minima we found, for example. And then by looking at the energy in all of those, we decided that this is the one which has the lowest energy. So that's as much as I'm going to say about geometric optimization. So just briefly about force constants and vibrational frequencies. So supposing we have, say, a carbon monoxide molecule. So you have two atoms, a carbon and an oxygen, and A is the equilibrium distance between them, and you change that equilibrium distance by some amount x. Okay, you either expand it or contract it. Now, what we could do is we can plot the total energy as a function of this extension x. So this is similar to, for example, the curves we got yesterday for silicon, the energy versus lattice constant. So if we look at where the minimum falls, that tells us the equilibrium bond length. And if you look at the curvature of this function, you can get the force constant k, and then you can get the vibrational frequency by omega equals square root of k over mu, where mu is the reduced mass. Okay. Alternatively, one could use the forces that act on these atoms when you displace them away from equilibrium. So here, this shows the force and this shows the extension. It looks almost linear, which tells you that this is almost quadratic in the neighborhood of small extensions. And by taking the slope of this, you can get the force constant, and then once again the frequency. Now, so in this simple case, we could choose to work either with the energy or with the forces. But supposing you have a more complicated case, for example, you have a triatomic molecule and you want to find the vibrational frequencies of this molecule, then supposing, for example, you displace this one away from equilibrium. If you just compute the change in energies, it will have entangled within it information about this force constant as well as this force constant, and maybe some bending mode as well. So if you wanted to disentangle all that information, instead of working with the energies, it would be useful to have the forces. So when you move this one in some direction, you would like to know what is the force exerted as a result on this one and on this one. And in general, one can do this for a crystal using what is called the frozen phonon technique. So this picture is supposed to be a linear diatomic chain which is vibrating in some transverse mode. And what you do in the frozen phonon technique is that you displace it by some amount using the eigenvectors of that vibrational mode. And you see how the forces change as a function of displacement. And from that you can get the phonon frequency for this mode. Nowadays, people tend not to use this technique as much because you can instead use density functional perturbation theory, which I think will be covered tomorrow. But so what you can compute if you know forces is what's called the force constant tensor. So if you displace one atom in some direction, you compute the forces on all your other atoms using the Hellman-Feynman theorem. And then this force constant tensor, you can build it up. It's the force induced on the jth atom in the beta direction when you move the ith atom in the direction alpha. So this is something that you can compute easily using the Hellman-Feynman theorem. Once you get these force constant tensors, which is information in real space, you can build up the dynamical matrix, and then you can diagonalize the dynamical matrix to get the phonon frequencies. And I'm almost done. I just want to mention very briefly that, of course, one very important thing that you need forces for is molecular dynamics. So if you have Newton's equations of motion, it tells you that the force on the ith ion is given by the mass times the acceleration, which is mass times the second derivative of the position as a function of time. So if we can compute the forces using the Hellman-Feynman theorem, then you can integrate these equations to get the ionic positions as a function of time. And there are different algorithms that you can use to do that, the Verdier algorithm, etc. And when you do that, you can do molecular dynamics, which will be covered next year. And questions?
So I think that people use a conjugate gradient method for the electronic state minimization. So what about for the ionic relaxation? Usually,
I guess the BFGS works better, so you usually use that. But you could choose to use conjugate. I don't think it's an option in the BWSCF code, but if you wanted to, you could use it. And which algorithm you use depends to some extent on your knowledge of what is the shape of the energy landscape.
Okay, the Newton method doesn't guarantee convergence if we don't have a good initial guess.
If you don't have?
We don't have a good starting position or good initial guess. So, yeah.
Well, sometimes, for example, when you run the PWSCF and you use BFGS, you do get to a point where you find that the BFGS isn't working well, so you find that instead of moving downhill, you move uphill, for example. And then what you do is you sort of do a few steepest descent steps to get back on the right path. Yeah.
Yes, in this presentation, you are talking about the global energy minimization, right? And you just give us an example about what you did. So you look at some configurations, and then you just compare with a model and get the lowest energy. So you then consider it as the global minimization.
No. So of course, there are more sophisticated techniques you can use, like simulated annealing and genetic algorithms, etc., which you can hope will help you find the global minimum. But as far as I know, there is no technique which will guarantee you that you have found the global minimum. So there is always this possibility remaining that there is some lower energy structure which you have somehow
right. That's just that's just right.
Yeah.
So we didn't just try every configuration, so we cannot guarantee that is the global minimization configurations, right?
Yes.
On this graphing sheet, what Anshan has done, so that has a periodic lattice, right?
Yes.
If you do the calculation, for example, in case of nanosystem, what kind of change in the input one is to get?
So you use a supercell, like I showed in my talk yesterday, where you include a vacuum region. Okay. And I think, is Nicola doing it?
Yeah,
we do it today, right?
Yeah. Well, there's lab, but
yeah, so we will do it today. Somewhere there is
Oh yeah, I just had a question about when you're doing geometry optimization. Do you generally try to start with the smallest unit cell, or do you try to start with something bigger? I mean, so essentially my idea, I'm just asking because if you have a large system, maybe locally, whenever you do your relaxation, you have different crystal structures that the bubbles compete, and so then it helps you find the global minimum there. Or is it just you want to do this as small as possible because it's expensive, and then compare
no, I didn't get your point. Why do you say it's better to use a bigger structure?
No, I'm asking if it's something that you feel and
so I mean, just as a practical matter, so say we're looking, okay, let's say for example in his case where he was looking for what happens when you have a vacancy roughly, maybe it's not a very good example because in that case, depending on the size of your unit cell, you are sort of constrained, so you can't relax as much. But supposing we had a very good one, big size, so we might choose to do the geometry optimization for that cell, and then use those coordinates as input for doing the optimization in a bigger cell. Is that what you're asking, or?
Yeah, yes, that was kind of what I was asking.
Okay, so we'll stop. Should we do a break or should we continue?
Do you want to reconvene at 10:30?